Let's continue the introductory training with an explanation of the modeling concept behind SimulationX. SimulationX uses the concept of lumped parameter networks. And in this section, I'm going to differentiate between signal-based modeling and equation-based modeling. For the physics-based calculations, SimulationX uses equation-based modeling. What that means is the calculation direction isn't always from input to output. It's not always in a specific direction. Instead, it creates a system of equations that, based off of the boundary conditions, can calculate the unknowns. To do that, potential and flow quantities are defined for each physical domain. Our models consist of elements and connections. The concept within SimulationX is such that in the connections, the potential quantities are calculated. It's where the conservation equations, like conservation of mass and conservation of energy, are calculated. Elements, on the other hand, define the relationship between flow and potential variables. So an element, for instance, could be a mechanical spring, or it could be a hydraulic valve. And based off of the potential variables in the connections on either side of that element, it's going to calculate the flow variables, whether that's force or mass flow or heat flow. Here's an overview of those different potential and flow quantities for some of the physics domains in SimulationX. We can see, for instance, in electronics, the potential quantity is voltage and the flow quantity is current. In mechanics, if we're using translational mechanics, the potential quantity is the velocity in the connection, and the flow quantity will be the force over the element. In fluid networks, the pressure is a potential quantity, and the volume flow or the mass flow is the flow quantity. And in thermal networks, likewise, the temperature is the potential quantity, and the heat flow is the flow quantity. So you can see that this analogy of potential and flow quantities applies to all of the physical domains. Within SimulationX, we have three types of modeling. The one we've described so far is network or equation-based modeling for the physics calculations. And this uses bidirectional connections or bidirectional flow of information. And in general, equation-based models look like the schematic diagram that you would see in a physics textbook. The next type of modeling is signal-based modeling, and that is for modeling of signal flows that we would see in a controller. In signal-based connections, the information flow is unidirectional. It's always flowing from the inputs to the outputs. The third type of modeling is text-based modeling. If you use the text view, you can represent your model in the Medelica language. Medelica is an open standard language maintained by the Medelica Association. Also, SimulationX has a tool called Type Designer that helps you code your elements in Medelica using a graphical user interface.